Yeah, so I'm here to present a talk. It's called An Internet of Peers. It's basically a talk about how we can make peer-to-peer networks that actually work. And we'll dive into that a little bit. So yeah, my name is Mathias. I go by Mathias on GitHub and Twitter. I have all my modules on the GitHub. If you want to reach out, just send me a ping. I live in Denmark. I recently bought a drawing tablet, so I've been spending a lot of time drawing. It's pretty fun. I live in Copenhagen, Denmark, which is actually not that far from here. It's only like a couple hours flight, so that's awesome. Spent a lot of time drawing this logo. This is where I work. It's actually not a company. It's a non-profit called DAT, which is a non-profit where we work on data science and building tools for sharing scientific data sets. It's really awesome. We basically just get paid to do a node and open source and peer-to-peer, which is like really, really nice. Very, very happy to be there. And it's a cool logo to draw, so that's awesome. Anyways, so let's get back to it. So basically, if you have a server, right? We all node people in here, or at least a lot of us are. And at some point, when you do node, the cool thing is like setting up some server, right? An HTTP server or something. And setting up servers in Node is really, really easy. And it's actually also really, really easy today to have people connect to these servers. So what do I mean by that? So we have this classic scenario where we have a client and a server. And there's a really cool laptop emoji now, but there's no cool server emojis. So I had to take the next big thing, which is like a printer, because it's like the only server you have at home these days. So you have this is like the classic scenario that most Node apps work by. You know, you have a client, and you have a server, and you connect to the client. The client connects to the server, right? And normally, the server has an IP. Here it's just like any IP, it's just a series of numbers, but and that's usually hidden behind some DNS record, but it all boils down to it having an IP. And then at some point in your code, you probably call something like .listen, and you listen on some port, and the port is also known. So you would have an IP, and you will listen on a known IP, and you will listen on some known port, right? Pretty straightforward. And then in the client, it's really easy because when the client wants to connect to a server, it's just going to use that IP and that port and just going to dial it up using TCP. And if you're writing HTTP servers, this is actually also what's happening underneath all the HTTP stuff. It's still just dialing TCP to an IP and port. And it's easy because it knows that the server lives there and has that port. And this works because the IP is not changing, because the IP is running, the server is running on some server, right? So it's probably running on Amazon, and Amazon gives you an IP, and they promise they won't change that IP. It's going to be stable, so you can point a DNS record to it. And also, the server is configured to actually accept incoming traffic, which makes things easy. So it's configured to accept a connection when it comes in for traffic and not reject it. I'm just going to keep track on time here. Okay, use my phone for that. That's easier. Cool. So that's awesome, except it's really, really boring. Because this has a bunch of downsides. For example, servers are single points of failure, right? So when you set up a server, when you turn it off, the server is not responding anymore. So that's a little bit sad, because that means that people can't access your website anymore, right? So that's a huge thing, and that's like we can mitigate this by adding more servers, but it's hard. Servers are also expensive. I used to run a startup where we had a lot of servers, so I know how those bills are not fun, because every time you set a server up these days, you basically have to rent it somewhere, and every time you set up another server, you have to rent another one. So just more and more money. And this is like a personal pet peeve of mine. It also requires something called ops, which is like a fancy word for people maintaining computers. Which is like really, really, it's like one of those things that got invented because of a problem. So we like build an entire industry around solving this problem, where like it would be nice just not to have the problem in the first place. So yeah, that's a little bit. So wouldn't it be better instead of having clients that connect to servers, if we had a scenario where clients just connected to clients, basically turn this arrow both ways instead of just one way, right? Have them both be clients. Because if they're both clients, we can easily expand this diagram to look like this, where you have clients connecting to other clients, and we can easily expand that diagram to look like this, where you have clients connecting to other clients, and just a whole network of clients connecting to clients. And then we get rid of the cost and the ops, because it's just other people's computers now, and we get rid of the single points of failures, because there's a lot of point of failures now, but it's just spread out, so that's awesome. So it's basically something we call a P2p network. Probably heard about that at some point if you ever use like BitTorrent or something like that. So I've seen this in a lot of talks. So it's very easy to describe something like peer-to-peer as just something that's better than centralized systems, right? Decentralized these days is always better than centralized because that's like the new hype and has a bunch of advantages, like I said. But it also introduces a bunch of really, really hard problems. This one is a really annoying one because it's something you don't really realize is really hard. But just, you have a computer, you have another computer, you want to send a message from one computer to another one. That's a surprisingly hard problem when we're not dealing with servers. And that's like kind of fundamental for writing any application these days. You probably want to send messages between them, otherwise it's not really decentralized. It's just, it's very decentralized because they can't even talk to each other, but it's not very fun though. And it's really hard because of these things. I don't know if anybody can guess what I'm trying to mimic here. Yeah, it's like firewall. There's no wall emoji, so you got to use the next big thing, which is a shield. I was kind of hoping they would add a wall emoji now that Trump got elected, but no. Anyways, so firewalls are cool because it's a security thing that makes sure that only people you have connected to ever can connect back to you, right? So it's a thing that just makes sure that people can't contact you without you contacting them. So if it's a phone, it just makes sure that you won't have like an annoying salesman calling you without you calling the salesman first, right? It's a good thing. It's a security thing, and it's enabled on almost all of our computers. And also, oh yeah, it kind of works like this. Made this little cool animation. So if you have a computer over here on the right that has a firewall, then you have a computer over here, and like this is like an annoying salesperson, and that person is trying to contact you without you contacting them. It kind of just goes like that. Like it hits the firewall, and then it just kills the message. So we have firewalls, and we all have firewalls on our computers. I actually think the MacBooks now come with the firewall turned off because I never ran into any problems there. But and also I think Windows does the same thing. But in your house at home, you probably have a router if you're connected to the internet, and the router always has a firewall, and that router also has its own IP, so that makes the problem even harder because that means that the IP of your computer is actually not the IP that other people see when they try to connect to your network because they got to go through your router first, right? So you can visualize that by applying a little bit of Unix foo. So if you run this first command here, ifconfig, and then some Unix magic, that'll print up your local IP, and then you can use an online service. And an online service will see like your router's IP because that's like the last point of entry before hitting that service, right? So we can just try and run this real quick, just for fun. So I have the two commands here. Let's just make this a little bit bigger. So if I run this command, this is my local IP, the IP I have on this network on my computer here. But if I contact a service and ask that service what my IP was when I contacted it, it tells me something different, right? You've probably already all seen this if you try to ever debug networks. But that's because that second IP is actually the IP of some router somewhere. So it makes it really hard to address this device here because there's like all these preliminary devices. That's why if you ever heard somebody talk about IPv6 and how IPv6 will make things easier for peer-to-peer, that's because we'll have so many addresses that we won't need like a router because we can just have everything have a unique address. The problem is basically that there's too few numbers to address every device in the world, so we need these intermediary devices, right? Cool. Yeah, so this makes it really, really hard to make peer-to-peer TCP connections, unfortunately. That's kind of sad because TCP is really cool. It's like one of those things you use that's actually a surprisingly good abstraction. You never need to know how TCP works. You just make a connection and you send data and the data comes back and it's like really nice. So the solution is don't use TCP, throw that out the window and use something else called UDP. Has anybody ever heard about UDP? Yeah, okay, cool. Cool people in this room. So UDP is great because it's stateless. So if you ever work with anything front end, you'll know that stateless is all the, that's where it's at now. That's how you get all the money. Stateless is good. So what I mean by stateless is that if you have a TCP connection, a connection has state. You're talking to somebody, you're sending messages. There's state that implies that a message sent after another message will arrive in that same order. It's like a lot of implied state. UDP has none of that. It's just a very bare-bone network abstraction that allows you to send messages to a port and IP, and that message might not even arrive, and messages might arrive out of order because it's completely stateless. It's just all the state of the thing you're sending is in that message. And the only thing it contains is it contains a payload that you're sending to somebody, and then your network stack will add an IP and port of the person to reply to. So if you get an UDP message from somebody, it's just like any arbitrary binary message that the other person sent you. It might even be corrupted. UDP doesn't even guarantee that. And then it also has an IP and port, so you can actually send a message back. So that's like a return address, but it's all embedded, so it's still stateless. Yeah, so here's an example of how that works in real life. So if you have a server and you want to send a packet, and you want to send you have a client and you want to send a packet and you want to send that to a server, and the server has an IP and port because it's still a server, and that's known. What you do is you send a message. It's a UDP message. So what happens is that message at some point hits a firewall, your router, for example. And then the firewall will look at this message, and it will look, where's this message going? Oh, it's going to the server. Okay, that's cool. So since you're sending a message to the server, I'm not going to allow the server to reply back to you because that's how most communication works. That's the contract. We're sending a message out. We want to allow the server to reply back because otherwise it's kind of useless. So then at some point the packet arrives at the server will look at it and reply back, right? And then all of a sudden now some message from the network arrives at your firewall, and the firewall will look at it, and it will look at where did it come from, which IP and the port did it come from. Oh, it came from the server. Oh, it's okay because we actually sent a message to that server earlier, so I'm going to allow it through. And then the message comes back to us. That's like basic network communication. And the cool thing is we can use this to trick firewalls into allowing arbitrary peer-to-peer connections from anybody in the world. And it's using something called hole punching. Because it's basically something that you try to punch a hole in the firewall. So let me try and explain to you how that works. So if you have two people, Alice and Bob, and they're on the internet, they have computers, but they're both behind a firewall, like most of us are. And they're not sysadmins, and they don't work in an ops department, so they don't know how to configure a computer. So it's all just standard configuration. So there's a firewall enabled somewhere, and they want to send messages to each other without going through a central server. How can they do it? Well, it actually becomes a lot easier if they just know a server by the IP port for a little while. Let me explain why. So let's assume they have a server they both know. So what they can do is Alice can send a packet to the server, and in this packet, it's a UDP packet. She says, hey, I would like to talk to Bob, right? So like before, this packet arrives at Alice's firewall, and this firewall will now allow the message server to reply back, right? Because that's how it works, like I explained before. So here's the trick. The server we're sending to is a special server. So it will look at Alice message and her current IP and port, because you always have an IP and port, it just changes once in a while. And then I'll write that down, like Alice's current IP and port is this address right now. So now there's, through firewalls, there's established a way where Alice can talk to the server, and the server can talk to Alice like before. It's basically just centralized communication. Nothing cool about that. But here's the cool part. We get Bob to do the same thing. So what he can do is he sends a packet to the server saying, hey, I'd like to talk to Alice. So now, same thing happens. The packet arrives at Bob's firewall, and this firewall will now allow the server to reply back to Bob. So the server gets a message from Bob. That message says, hey, I'd like to talk to Alice. But the server already talked to Alice, so it has her current IP and port. So it does this cool thing where it replies back to Bob with Alice's current IP and port. So now Bob gets this IP and port back, and he just tries to send the message to that IP and port, which is Alice. So this is kind of sad because, well, this cool thing happens first where this message will pass through Bob's firewall, and he's sending to Alice. So now the firewalls will allow Alice to reply back, right? But the message arrives at Alice's firewall, and since Alice has never talked to Bob before, it'll just drop it. It'll be like, this is probably a salesperson trying to sell us cheap crap. Fuck that, and then throw it away. So it doesn't work. But we now established a way where Bob can receive messages from Alice because the message passed through his firewall. So at the same time, the server sends a message to Bob to try to connect to Alice. The server will just do the same thing to Alice. Tell her, hey, here's Bob's IP and port. Could you try and connect to him? So we'll still send a packet to Bob. By doing that, her firewall now allows messages to come in from Bob. And by doing this simple trick, we actually established a way where Alice and Bob can now talk directly to each other because we opened their firewalls to talk directly to each other without talking to the server, so we can just drop that server. So this connection is called hole punching. It's like an easy 17-step guide to peer-to-peer connectivity. And the cool thing is that it works on most networks and most firewalls because this is basically one huge hack. There's like firewalls configured to really shut it down. So to test how many networks this works on, I wrote a little tool. You can actually install it. It's called peer-to-peer test. And if you install it from npm, you can run it with a, you don't even have to, but if you want to, a short description of your network, then it will just do a test by pinging some servers to figure out if you can actually support this kind of communication. So we can actually try and run this on just this network. So if I run, this, I'll get this response back where it says it's hole punchable true because it actually passed the test for being hole punchable. So this network we're on here actually allows us to connect peer-to-peer to other people, which is kind of awesome. So if you run that, you'll help me collect more data. I have this cool map that's live updating every time somebody runs it. The poop means that hole punching didn't work, and the thumbs up means that it worked. So you can kind of see here, unscientifically, the ratio between poops and thumbs up is around, it's probably around 80, 90% that works. So 80, 90% is actually not that great if you think about it, in terms of user experience. If you're connecting to somebody peer-to-peer, right, and in 10% of the cases it doesn't work, that's it's a hard sell. So what you need to do is you need to build peer-to-peer networks where you, instead of just trying to connect to one person, try to connect to 2 or 3 people like you do in BitTorrent. Because then, if you've done a little bit of statistics, then those 10% very quickly turn into 0.1%, and then the more people you add, it just exponentially goes down the chance of failure. So if you just have a network where you try to connect to 5 people, there's a very, very high chance that will actually work. So it's actually really cool. Oh yeah, I had a couple of friends of mine send me pictures while they ran it. This is my friend Emil, who was in Australia by the kangaroo sign. He ran it. You can see here that hole punching actually worked in Australia, so that's kind of cool. I got this picture from Africa with somebody on a safari, my friend Richard actually, who ran it, and yeah, it's also hole punchable, even though there's a cheetah. I wrote this picture this morning, like my imagination of what happened after he took that picture. Probably got eaten, and then there's a cool cheetah with a laptop somewhere. Yeah. Anyways, so this all it's a really extremely powerful, very simple technique to actually connect people together. The fundamentals of all P2p networks. The only problem is that this basically means that we can't really use hostnames and port to describe computers because hostnames and ports change in these networks. So we have to use something opaque like a name to describe services instead. And you need to resolve that name to peer somehow. So this is like, what DNS does in normal systems. But in a P2p network, we would use something called DHT, which is just like a fancy word for decentralized DNS, basically. So something where, instead of listening on a port, you will listen on a name, and then it would pick a port for you and send that to a network. And then other people would find you by doing a lookup for that name, so that would return potential peers. And then you would have a security network on top of this that would allow you, to filter out bad actors. For example, you could connect to a public key and then require the people that are listening on the public key to do a cryptographic proof. It's a very common technique. Let me just check the time real quick. Cool. Yeah. Also, this technique, hole punching, only allows you to send UDP messages, which is not really useful. I don't know how many UDP services you ever created in your life, but the only ones I've done was like basically DNS. And in Node, we have this cool thing called a stream, which is like what HTTP is and what TCP is. And we want to deal with streams instead of UDP messages because we want to actually send streams of data. So you can use something called UTP. It's very confusing for people who don't speak English that somehow they chose to name all these things the same three-letter combination, but switch out like T's and D's, which to me sound the same. But UTP is something that upgrades a UDP socket to a reliable stream. It's like a TCP connection, basically. It basically turns UDP into a TCP. And I wrote bindings for this. It's called UDP native, and you can use it today if you just install it. But we kind of want to take, all of this crap and just bundle up to one big packet, so we don't have to deal with hole punching, DSTs, and UTP. We just want to, have it all be one thing we can just use as a single network. And I wrote that. It's called P network, and it's something I use a lot at work. And I'm gonna try and do a demo of that now. So it's on npm. It's on npm. It's on GitHub also. It's a very simple thing that basically just, my build error, so it probably doesn't work. Let's see. Anyways, it's a simple thing that basically just has the same interface as TCP, but it uses all these techniques instead. And instead of listening on ports, you have to listen on names. And instead of connecting to ports, you have to connect to names, right? So I wrote this example earlier. Let's see if it works. So here's a server. Let me open that up in an editor so it's a little bit easier to grok. I can just turn this light properly. Is this light? Oh, that's worse. Now the next 10 minutes of my presentation will just be me going through colored schemes. Eiffel, that sounds light. There we go. So it's basically, it's the same interface as TCP or HTTP. You just create a server. This is a server. It just hooks up to standard input and writes that message. Every time you type on standard input, it'll send a message to the socket. And every time there is a message, you'll write it out. And then when you shut down the program, it'll just close the server to be nice. You don't have to do that. And here's a client that does the same thing. So it's like classic server client terminology still, which is like nice because that's what we want. That's like how the world works. So what I can do is, let's see if it works. I have no idea. I can run a server, and just by default it just listens on example. And then I can run the client. I just hacked this demo together just before the talk, so if it doesn't work, bear with me. So it works locally, which is cool. It's actually still using a DHT. The DHT is just that fast. If I type something here, it goes to the server, because it's, and if I type something on the server, it goes back again. But the cool thing is that it does hole punching, so let me try and showcase that. So of course it works locally. It's very easy to write things that work locally. So just try a demo that has like a high chance of failing, but it also has a chance of working, so that's fun. Where I run a server locally, I'm going to call it demo, and then on this computer now it's running a server. I'm now going to go to another machine and have another machine act as a client. So since my computer is acting as server, my computer now has to support hole punching to accept connections, because between here and there's a bunch of firewalls, right? So if I go to this other server and go into the folder, it's just the same code. I have a client here. Oh, I need to go into example. Typing, it's hard. Same client. So if you try and run this demo. So it's actually a hole punch now, and the local server that's running on my computer can actually accept connections from the outside world. And I can, that doesn't work for some reason. There's a bug in UTP where you have to have the client type the first message for some reason. I don't know why. They actually do hole punching this way, as explained. So actually what happened here in this, if I run this again, what actually happens here is it actually, contacts the DHT, gets a list of peers back, look at that list of peers, try to hole punch to them by, doing those 17-step program I talked about, with sending a bunch of messages, connecting, and then it actually worked. And you can scale this up by just running more servers, which is kind of fun. I haven't tested this yet because I just edited this, so let's see if it works. So if I run 2 servers, I wonder what happens. Then it just picks one of them. So it actually it load balances for you also, because it just takes a random one on the list from the DHT. I need ways to configure that. Anyways, yeah, so it's very, very simple. It's very easy to use. It just uses my DHT per default that I'm hosting, that other people can join. Like every time you run this program, it's also joining the DHT, so it's making the network stronger. So that's really, really useful, and it's a very powerful technique. Yeah, that's it. Thanks. I learned how to pronounce this, but now I forgot, and I'm not going to try it because I forgot how the letters are pronounced. But this is kind of cool because the Y kind of looks like a beer icon, and we're getting beers later. So I just wanted, that's awesome. Anyways, I think we have time for a few questions, right? Yeah. Anybody have any questions?
Yeah, hi.
Hey.
And what server do you use for hole punching in your demo?
So I wrote this module a while ago called Hybrid DHT, which is, are you familiar with DHTs? A little bit. Everybody's, yeah, that's like my same. So there's this really cool DHT model called Kademlia, which is actually, if you ever want to read a scientific paper, read the Kademlia paper, because it's like a paper that's 5 pages long, and you can actually understand it while you read it without being a university professor. And it explains how you can make an insanely scalable network using a DHT and how to implement it. And I implemented that in a module called DHT RPC, which is just like it's basically just a module that does RPC over let's see if it loads. Also doesn't matter. It does RPC over a DHT basically. And this hybrid DHT and then implements a few RPC calls to do the hole punching. If it loads, I'll show you. But the cool thing about it is that you can actually implement Kademlia and like, I think it's 300 lines of code, something like that. So it's like very powerful, very small. So I run a Bootstrap server, actually a series of Bootstrap servers. We can just see that So I run one called Bootstrap 1, but I actually have 3 of them. I just only added one for this demo because in case of networks and stuff like that. But every time you run one, you join the network. You join the DHT. But the only thing that Bootstrap does is that's the server context first to introduce to other servers. So to answer your question, the server it does the hole punching through is actually just the server in the DHT that's nearest the client you're trying to connect to. It's a little to make it scalable. So that means that if you have 1 billion people trying to connect to each other, that load will actually spread out through the network, so they'll all contact different servers. Depending on how big the DHT is, it'll spread the load uniformly over that DHT. So if the DHT has 20,000 nodes, for example, the BitTorrent DHT has 20 million nodes. So if you had a DHT that big, it would load balance that traffic over all those nodes. The only thing you need to do hole punching is just a server. If you and I wanted to hole punch to each other, the only thing we needed is a server we can both connect to without any hole punching, and a server that we both know about. And actually, those 2 exact things is what the DHT provides us with at a low level. So that's why I kind of cut the connection. So you don't even need centralized hole punching. You can spread that out. So just to finish that, something they never tell you about hole punching is that if you use something like WebRTC, for example, right? You also hole punch. That's how it does. It basically does the same thing. But the thing they never show you is how do they hole punch? They hole punch using a centralized infrastructure. Who hosts that centralized infrastructure? Well, if you never put in a server in your code, which you probably didn't, it's probably contacting one of Google's servers because Google have a huge infrastructure for that. So that basically means that Google knows who's connecting to everybody. It's leaking a lot of metadata actually. So by using a DHT, we get to spread that load out, so there's like no central honeypot that can just collect all that data. So it actually has it's scalable and has a bunch of nice privacy features also. And you can use your own if you don't want to use mine. Mine is just nice for demos because then I don't have to type in anything.
Okay, I also have one question. Obviously you're doing all these things to solve some business problems, right? So can you share with us what actual problems you're solving with this?
Yeah, sure. So the project I'm working on is called that, basically. And it's just a file sharing tool for sharing large pieces of large data sets. And it's basically just a command line tool. I have my own client called that next because we have one called that, and then we have one called that next, which is like experimental, and then I have my own experimental one that's called that next. Anyways, so just to whoa, crazy output. I did some debugging earlier. Whoa, there we go. So basically what that does is blah, 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 it builds a file sharing system, and at some point it creates this cryptographic proof that if you share this key, other people with the same key can verify the data, right? But people have to find each other to share this data. So what we do is we actually use this key as a name in a peer network. Then other people can find other peers sharing the same data set. This is this key identifies the data set, and it also identifies the data. So you can connect to a bunch of people, and there's basically the module underneath verifies that the traffic is correct. So you can just try to connect to everybody in the world. But that peer network makes it very easy to facilitate all those connections. But you can I have like a gazillion other modules on NPM that uses this to do it, including some fun live streaming ones. I wonder if I can see that there. I'm just curious now if other people use it. Anyways, so there's 22 modules using it. A bunch of these are mine. But yeah, so basically we use it to bootstrap a file sharing network. But you can use it to bootstrap any kind of traffic where you have an identifier that can describe your thing. Yeah. I also have another use case, actually, now I just think about it, is that I use this also for a build cluster at home, where I have Windows machines announced themselves as Windows machines and Unix machines, and then I can route traffic to them and have them build native modules. Did somebody raise their hand here? No, maybe.
So, any questions? Okay, yeah? Oh, there, that way.
Also, if you want to talk more about use cases and how it works, just ping me after. There's like a million ways you can use this.
I've been wondering, for instance, if there are two clients behind a router network.
What? Can you say that again? Sorry.
If there are two clients behind a router network, how can?
What? Sorry.
If there are two clients.
Two clients. Yeah.
Between under the router network. During the hole punching, you use the router's IP address and the port.
Yeah.
How can you establish network from the third client to the both of the first two?
Yes. So that's a really good question. So actually, it's a surprisingly fun problem. So hole punching, if you have, I noticed on the hotel network here, the hotel network actually bans local traffic. So if I have a computer, I have two computers on this network, I can't even connect directly between these computers because they have a very strict firewall. And the funny thing is that in those situations, if you have two computers on the same network, the same public network, hole punching actually doesn't work because it only works between different networks. So you need to have different techniques in play to ensure that local traffic works. It's kind of very counterintuitive, for me at least, that local traffic is harder to hole punch than remote traffic, because remote traffic is an inherently harder problem. So what we do is, with local traffic, we actually just try to connect, and if that doesn't work, we just fail. And in our use case, we will then, at the end, try and fall back to something like a proxy service to connect it, where traffic is routed through another peer. Our traffic is end-to-end encrypted, so we wouldn't leak any data by doing that. But you would have to implement that yourself. So the peer network, actually, what it does is that when it announces its address, it also announces its local address. And if you talk to a DHT node and you opt in to sending your local address to it, it will look at the addresses it has cached. And if it has local addresses cached with the same first part of the subnet, it will send those back also, because there's a high chance that they will work. But yeah, it's basically just a bunch of hacks that sometimes work. But we only had, it's like I said, it's a probability game. So as long as there's like 5 people on the network, if there's like 5 people on the network and you have 50% chance of it's working, it's like it's like gonna use JavaScript to do math. That's always a bad idea. So that's like a 97% chance it'll work then. And this works in, like I said, 80% of the cases, so that probability is even better. So yeah.